Up to now, we've either looked at a rotational or a vibrational transition, and we've looked at pure rotational and pure vibrational spectrum. But in actual fact, molecules both vibrate and rotate at the same time, and when they transition from one state to the other, they can change their rotational and their vibrational quantum numbers. And this gives rise to a Ro-vib, or a rotational vibrational spectra. We've seen before that almost all molecules will be in a ground vibrational state. So that means for absorption, then we are going to be going from V equals 0 to V equals 1. So we're going to assume it's going to be a harmonic transition here. It's quite common actually to use a prime and a double prime notation. We use the double prime for the initial state, and we use the single prime for the final state. So for absorptions, we're always going from a double prime to a single prime. Now for rotational states, they're not necessarily in the ground vibrational state, so they can go up or they can go down, and delta J can go either up by 1 or it can go down by 1. So we see both those possibilities, it turns out. We can go ahead and we can draw a diagram that kind of shows this going on. I'm going to draw my energy here on the left hand side, and we're going to start off with vibrational states. So we've got V double prime equals 0, so the double prime is for the ground state, and we're going to write a single prime for an excited state. Most of the molecules are going from the bottom to the top. If this was just an if this was just a vibrational transition, this would be all that we would see. On top of this, however, we've got rotational states, and so we can go ahead and write on the left hand side the rotational levels. So J double prime corresponds to the initial state, and J single prime corresponds to the final state. When J equals 0, we have no rotational energy, so essentially we are exactly over top our vibrational energies. And as we go to higher and higher levels, so when J double prime is 1, or is 2, or is 3, or is 4, we can add that rotational energy to that vibrational energy. And the same in the excited state here. So the prime state, so J prime equals 0, and J prime equals 1, and 2, and 3, and 4 looks something like that. So we've said that our selection rule is that delta V has to go either up by 1 or down by 1. For absorption, though, essentially we're just going to go 0, 1. Almost all the molecules are in the ground vibrational state, V equals 0. But for rotation, we can go either up by 1 or we can go down by 1. And in a pure rotational spectrum, our only possibility is probably to go up by 1. But we can see here that we can actually go either up or we can go down. I'm going to go ahead and draw these lines in green. So let's go ahead and examine delta J going down by 1. So we can imagine starting from this line and going to this line here. So this is J double prime equals 1, going to J prime equals 0. So we're going from 1 to 0. We also have the possibility of going from 2 to 1, and the possibility of going from 3 to 2, and from 4 to 3, and so on. And we can sort of intuit here that these green lines here are getting shorter and shorter, so they correspond to lower and lower energies. In fact, we call this, when J changes by -1, the P branch. And so in our spectrum, that these lines here are referred to as the P branch lines. Now going in the other direction, so we can change J, we can actually increase J by 1. This is referred to as the R branch. So if we're going up by 1, that means we can start at J double prime equals 0 and go to J prime equals 1. We can start at 1 and go to 2. We can start at 2 and go to 3, and 3 and go to 4, and you can probably intuit here that we are actually going up to higher and higher energies than where we started with, rotationally speaking. So these lines are going to have more and more energy, greater wave numbers, greater frequencies, whichever unit you prefer to work with. It is conventional actually to label these lines with the initial state we started with. So our first P line here, we would name P1, and then this one here would be P2, and the one next to it we would label as P3. So we're starting at 1 or 2 or 3 respectively here. And on the other side, of course, we can start at J double prime equals 0 because we're going up. So this is R0 when we start at 0 and go to 1. This one here we would label as R1. This one here we would label as R2. So we start at 2 and we go to 3. Of course, there is no P0 because if we're going down by 1, we can't start at 0 and go to -1. There is no J equals -1 quantum number. So if we want to go ahead and predict what the spectrum looks like, we can just kind of shift this up for now, and we can draw the spectrum along the bottom here. We're going to go increase in wave number from left to right. On an infrared spectrum, it's normally plotted in the opposite direction, so we have to remember to kind of reorient our brain sometimes. The R branches here, we're going to higher and higher energy, so these lines would lay to the right. So we can go ahead and we can start and draw the R0 position, and that's corresponding to J double prime equals 0 to J prime equals 1. We could go ahead and draw R1, and that's the 1 to 2 transition. And next to that, we would have R2, that would be 2 to 3. And next to that, we would have R3, so that would be 3 to 4. And if we had the other lines, they would be alongside and look something like this. And in the center here, actually, we have the natural vibrational frequency here. So this is 1 over 2 pi c root k over mu. And on the other side, since our P branch is going to lower rotational quantum numbers in the upper state, these lie to lower wave numbers of our natural vibrational frequency. So P1 is our first line. This is going to be the 1-0 transition, and so on. So we've got P2, P3, P4, P5, P6, going from 2 to 1, and 3 to 2, and 4 to 3, and so on. So we've got all these extra lines here in our spectrum. And this looks just like the pure rotational spectrum, except we've got one on the right and we've got one on the left, centered around the natural vibrational frequency. So we can go ahead and we can label these. So again, this is the P branch on the left and the R branch on the right hand side. And so the R branch is when we've got delta J going up by 1, and the P branch is when we've got delta J going down by 1. We normally don't see anything in the middle here, but every now and again we get molecules that have lines in the middle, and if we've got P on the left and R on the right, this one in the middle here we would refer to, if it were present, as the Q branch, and the Q branch corresponds to no change in rotational quantum number. And we see that sometimes for polyatomic molecules, so we've restricted ourselves to diatomics, but if we've got more than 2 atoms, right, we would have the possibility of this Q branch. And also we can see molecules like NO, nitric oxide, actually has a Q branch, and it turns out when we've got unpaired electrons, we often see a Q branch in our spectrum. A couple of other things to mention here, since we've essentially got our rotational spectrum overlaid on top of our vibrational spectrum. The spacing is 2b, where b is that rotational constant, so it should be the same on both sides. Although we'll see that if we've got centrifugal distortion, it's actually a little bit bigger on one side than the other. We also see that envelope, right? So we said before that the rotational quantum numbers, as we go to higher and higher levels, there's less probability of being up there, but there's more levels. The levels increase by 2j plus 1, but the populations go as e to the minus that energy over kt. And so we also see this sort of envelope letting us know what the rotational populations are like. This is a infrared spectrum from hydrogen chloride. This is from the NIST chemistry webbook, and if we kind of zoom in here, we can see the P and the R branches here. So let me go ahead, let me zoom back out right there a little bit. It's conventional, of course, to write the wave numbers increasing from right to left in infrared spectrum. So we have our P branch here on the right-hand side, corresponding to delta J going down by 1. Of course, also we've got delta V's going up by 1 because this is an infrared absorption. And on the left-hand side, we've got the R branch, and the R branch is where we've got delta J increasing by 1, so it goes to a higher and higher energy, so a higher and higher wave numbers here. And of course delta V has to go up by 1 for an absorption. And we can see the lines here, so the lines here have that very nice spacing, and if we could zoom in and read, we could go ahead and we could calculate that spacing, that's 2b, and of course we could relate b to things like the bond length, okay, or the bond strength, the force constant K, or the reduced mass. If we knew 2 of those, we could use it to calculate the third. Notice in the spectrum here, there is no center here, so you can see there is sort of a line in the center, right, where there's an absence. So there is no Q branch in hydrogen chloride. HCl is a diatomic, it has no unpaired electrons, so we don't expect to see a Q branch in this molecule. And we can't really see it on this spectrum super well, but when you do this in the lab, and it's really a shame we didn't do this lab, these lines themselves are actually doublets. They're actually split, and sometimes they're not very well resolved. They might look something like so. And if you've ever looked at these and you're like, well, why are those lines not nice and sharp? Why are they actually split? What you're seeing are the two different isotopomers. So we've got chlorine 35 and we've got chlorine 37. And so when we have hydrogen chloride, we actually have a mixture of these, and it's approximately a 3-to-1 ratio. So we're looking at percent transmittances here. So percent transmittance is normally plotted in vertical direction. 100% would be at the top, 0% would be at the bottom. So this corresponds to an increased absorption and with a lower percent transmittance. And as more light is transmitted, this one here corresponds to a lower absorption, a higher percent transmittance. And we know Beer's law says absorption is proportional to concentration. So it turns out that those deep peaks there are actually coming from the hydrogen 35 isotopomer, and those shallow peaks there that corresponds to high percent T's or low absorptions are corresponding to the chlorine 37 isotopomer.